everyone, let's solve a problem from GATE 2023 Aerospace Engineering paper, question number 58, right? So the question is, entropy is defined as the square of the magnitude of the vorticity. For the three-dimensional velocity field, we have been given a velocity field. The entropy at the location 1, 1, 1 is dashed, right? So the velocity field which has been given, so here u is 4x minus 1.5y plus 2.5z and v is 1.5x minus 1.5y and w is 0.7xy, right? So we just have to find the entropy at the location 1, 1, 1. And we have also been given that the entropy is the square of the magnitude of the vorticity, right? We know that the vorticity is the curl of velocity vector. So we will first find the curl of velocity vector and then we will just find the magnitude of that vorticity and we will square it, which will give us the entropy, right? So the NPTEL reference for this particular question is from the course Fundamentals of Theoretical and Experimental Aerodynamics by Professor Arnaud Roy, and the particular video that you want to have a look at for this question is from week 2 lecture 9, Irrotational and Rotational Flow, Strain of a Fluid Element, Gradient, Divergence, Lines, Surface and Volume Integrals. You can see the YouTube link of that particular lecture also here, right? Now let's go solve the problem. This is the velocity vector that has been given, and I have just splitted those velocity component, each velocity component as u, v and w. Now we will first find the vorticity, magnitude of vorticity, and we will square it to get the entropy, right? First, to find the magnitude of vorticity, so the vorticity vector is defined as the curl of velocity vector, right? Which is nothing but del vector cross product of del vector and the velocity vector, right? J, K, right? Dou by dou y, dou by dou z, u, v, w are the velocity components in x, y and z direction, right? Now if we find this, we will get I into dou w by dou y minus dou v by dou z, right? Minus j vector into dou w by dou x minus, this is dou w by dou x minus dou u by dou z, right? Plus k vector into, we will get dou v by dou x minus dou u by dou y, right? So this is what we are getting. Now let's just substitute the values for that. We just have to differentiate w with respect to y. So this is our w. If we differentiate with respect to y, we will get 0.7x minus, we have to differentiate v with respect to z. We have v here, we don't have any z in the function, so this will become 0, right? So j into, we have to differentiate w with respect to x, and we will get 0.7y minus, and we have to differentiate u with respect to z. So we have a z component here which is 2.5, so we will get 2.5 once we differentiate. So k, so we have to differentiate v respect to x, right? We have only one x component, then that will come out to be 1.5 minus, we have to differentiate u with respect to y. So we have a u where we have a term of minus 1.5y, So upon differentiation it will become plus 1.5, right? So now if you substitute 1 at 1 comma 1 comma 1, we will get 0.7 I vector minus, so here we will get 1.8, right? Minus 1.8 we will get, so that will become plus 1.8, 0.8 j vector plus 3k vector, right? So this is our vorticity at 1 comma 1 comma 1. So we will find the magnitude. In order to find the magnitude, we will just have to take 0.7 square plus 1.8 square plus 3 square, right? Now if we want to find the entropy, which is omega square, so if we take the square root, then we will get 0.7 square plus 1.5 square, 8 square plus 3 square, right? So which will, if we find the value, which will come out to be 12.73. This is our entropy value for this problem, right? So here the square root get cancelled when we square the vorticity, right? So this is the answer. Let's go back. So the entropy at the location 1 comma 1 comma 1 for this particular velocity field is 12.73. Okay, that's all for this question. Thank you.